Hello and welcome to this session, Learning Outcome LO3. Understand the structure of matter. Today, we will learn what lies at the heart of everything around us. By exploring the structure of matter, we can see how different particles come together to form all materials. We will look at the fundamental particles that make up matter and examine how their arrangement and movement differ in solids, liquids, and gases. All matter consists of tiny particles like atoms, ions, or molecules. The particle model explains their behavior in different states. It focuses on their spacing, attraction, movement, and energy. This model helps us understand phenomena like expansion and diffusion. Despite its simplicity, it describes everyday behaviors effectively. In solids, particles are tightly packed in a fixed structure. They can vibrate, but not move freely. Strong forces of attraction keep them in place. This is why solids maintain a definite shape and volume. Their rigidity is due to this fixed particle arrangement. Particles in liquids are close, but not in a fixed pattern. They can slide past each other, making liquids flow. The forces of attraction are weaker than in solids. Liquids retain volume but take the shape of their container. This flexibility is due to their particle arrangement. Gas particles are far apart with minimal attraction. They move quickly in all directions. This allows gases to fill any container and be easily compressed. Gases have no fixed shape or volume. Their behavior explains why they expand readily. Heating or cooling matter changes particle energy. This leads to changes in state like melting or boiling. During melting, particles gain energy and break free. In condensation, they lose energy and come closer. These are physical changes affecting particle arrangement. Density measures how closely particles are packed. Solids are usually densest, followed by liquids, then gases. This explains why objects float or sink. Gas particles being further apart result in lower density. Density differences also explain why hot air rises. Diffusion is the spreading of particles from high to low concentration. It occurs fastest in gases due to particle speed. Liquids diffuse more slowly, and solids hardly at all. Examples include perfume spreading in a room. Diffusion demonstrates random particle movement. Internal energy is the total kinetic and potential energy in a substance. Kinetic energy arises from particle movement. Potential energy comes from attraction forces. Heating increases internal energy. Cooling reduces it. This concept links to temperature and state changes. Tensile stress is the force per unit area when a material is stretched. It measures how much pulling force a material experiences. The formula involves force and cross-sectional area. Tensile stress helps understand material behavior under tension. It is crucial for engineering and construction. Compressive stress occurs when a material is squashed. It uses the same formula as tensile stress. However, the material is shortened instead of lengthened. Structures like columns and bricks handle compressive stress. Understanding this helps in designing stable structures. Strain measures how much a material changes in length under force. It is a ratio, not a force. Strain has no units, showing deformation relative to original size. This helps in understanding material flexibility. It is crucial for assessing material performance. Strength is the maximum stress a material can withstand before failure. It includes tensile, compressive, and shear strength. Strength indicates material resistance under different conditions. Knowing this helps in selecting materials for specific applications. It ensures safety and durability. Breaking stress is the stress at which a material breaks. It corresponds to the fracture point on a stress-strain graph. Once reached, the material cannot carry more load. Breaking stress is slightly lower than ultimate tensile stress. Understanding this prevents material failure. Stiffness measures how much a material resists deformation. A stiff material does not easily stretch or compress. It differs from strength, which is resistance to breaking. Stiffness relates to bending or stretching under load. This property is crucial for structural applications. Young's modulus is the ratio of stress to strain in a material's elastic region. It measures elastic stiffness. A high modulus indicates a stiff material, like steel. A low modulus means flexibility. Like rubber, Young's modulus is vital for understanding material elasticity. Dislocations are defects in a material's atomic structure. They affect mechanical behavior, making metals bendable. There are edge and screw dislocations. Controlling dislocations adjusts material strength. This is crucial in processes like work hardening and alloying. Understanding crack propagation aids in designing safer structures. Crack propagation is how cracks grow under stress. Sharp cracks increase stress concentration. Brittle materials fail suddenly, while ductile ones show warning signs. It is essential for material selection and failure prediction. Elastic distortion is a temporary shape change under force. The material returns to its original shape once the force is removed. Young's modulus governs this behavior. High modulus means less distortion, low modulus more. Elastic distortion stops at the yield point, beyond which plastic deformation occurs. Understanding material properties is crucial for engineering. It informs the design of buildings, machinery, and everyday products. Selecting the right material ensures safety and efficiency. Knowledge of stress, strain, and elasticity guides material choice. This understanding is foundational in physics and engineering. For more in-depth knowledge, refer to recommended books and journals. They provide detailed insights into material physics. Online resources also offer valuable information. Exploring these materials enhances understanding. Continuous learning is key to mastering this subject. In conclusion, understanding the structure of matter helps explain how particles determine the properties of different materials. Whether in solids, liquids, or gases, each state is defined by its own distinctive particle arrangement. This understanding is fundamental to disciplines such as engineering and physics, where material behavior must be accurately predicted and applied. For any queries, please reach out via WhatsApp on 0748436168 and one of our team members will assist you. We look forward to seeing you at the next session.